So welcome back to our last chapter in Calculus 2. So far in chapter 11, we looked at ways that we can take functions that we're familiar with, such as sine, cosine, and e to the x, and actually write it as a polynomial. Because as we all know, polynomials are so much easier to work with. So it's representing a function in a different way. So what we're going to continue that idea in chapter 12, and what we're going to do is come up with different ways to represent a relation. In this first case, under parametric equations, so there's two parts of chapter 12, parametric and then polar. We're going to start with our parametric, which is 12.1. And here's, in a minute, you'll find out why. Why do we need parametric equations? But I want to start with something you know, because you have been working with parametric equations. And I want you to go back to trigonometry and specifically the unit circle. So let's draw a basic unit circle, right? So we know our unit circle is a circle of radius 1 centered at the origin and is made up of x, y points. So what do we know? Let's just kind of review everything we know about this unit circle. First of all, you know the equation of a unit circle, right? If you recall from some of your pre-calc classes, a unit circle centered at the origin, so it's not x minus anything, it's just x squared plus y squared equals r squared. But since it's a unit circle, the radius is 1, x squared plus y squared equals 1. That is our standard equation for a circle. Now, let's go back to trigonometry. What do we know about those x and y values? So in trig, what we did is we started with angles. We raised our angles from the positive x-axis, right? Let's, for the sake of what we're doing with parametrics, normally we would call that angle theta or alpha or beta or something like that. I'm going to actually call the angle T. Okay? I'm going to call that angle T. And in your trig class, your pre-calc 2 class, if you took it at Raritan, what you learned, and see if you can remember, x is equal to cosine of that angle, and your y value is equal to the sine of that angle. And that just comes from our basic right triangle trig, right? Because cosine is adjacent over hypotenuse. The adjacent is going to be the x value of that point. Hypotenuse, of course, is 1. And then sine is opposite, which is our y distance over 1. So that's where we get the x. So this is something you're all familiar with. Okay? X equals cosine t, y equals sine t. Now, each of those represent a graph on their own. So let's start with the first one. X equals cosine t. So now, that is our standard cosine graph. But when I make this cosine graph, let's get away from our x and y axis as we know it. This is now becomes our t-axis, because, or alpha or theta, if you were using angles notation. And our y-axis is now our x representation, because you would know this particular function is y equals cosine t. But because it's over here as x equals cosine t, all I'm doing is renaming the y-axis as an x-axis. Okay, and then I can draw the graph at 1, and I can, you all know what your cosine graph is. Right? It goes like this. Okay, and here we are at pi. No. Let me fix it. Hold on. There we go. I'll make it a little bit longer. And this brings us to 2 pi, and here we are at pi. And then, of course, we could also do y equals sine t, and you know that one as well. This, again, would also be my t-axis, and this would be my y-axis. Okay, so think about this a minute. Again, this is stuff you learned in your pre-calculated trigonometry course. We've taken a unit circle, created 2 functions out of 1 point, or this entire circle. We've created 2 separate functions, x equals cosine t and y equals sine t. We're going to define t. We're going to keep it simple and just be between 0 and 2 pi. Okay, so what we have here is what we call parametric equations. So think about what's happening. We take our x and y value that we know is this, and we separate it and relate it to a third parameter. In this case, the parameter is t, but it represents the angle. So what that means is, as you go around your unit circle, there is a specific way to write x and y as they relate to the angle t. X is always going to be cosine t on a unit circle, and y is always going to be sine t. If we move away from the unit circle and become, you know, a larger radius, all that's going to do, and we'll get to that in a minute, is the coefficient in front of cosine and sine would no longer be 1. You know, if the circle had a radius of 2, there'd be a 2 in front of there. If it had a radius of 5, there'd be a 5 in front of there. But I want you to stop and think and just review what you've already learned and understand this idea of parametric equations. So here's the question. What's the point? Why would we take this nice, simple equation of x squared plus y squared equals 1 and break it off, which is essentially what we did, into 2 separate graphs represented by 2 separate functions? So let me say that again. Why are we taking this equation, x squared plus y squared equals 1, and rewriting it as x equals cosine t, y equals sine t? Because they represent ultimately the same thing. Even though on their own, your x equals cosine t is a curve and y equals sine t is a curve. Why do we think this is important to do? Well, look at the pictures. Look at the circle versus these 2 curves. What do these 2 curves have in common that the circle does not? And if you thought function, you are correct. When you have a curve that is not a function, such as a circle, that limits us in what we can do with that curve when it comes to derivatives and integrals. By breaking or rewriting our non-function, x squared plus y squared equals 1, into 2 functions, because look at that, x equals cosine t, that's a function, y equals sine t is a function. What it does is gives us a new way to represent our non-function as a pair of functions. That's what parametric equations do for us. Okay, so that's the importance of them. Parametric equations, if you're moving on to Calc 3, you are going to use a lot of parametric equations. We have worked so far in everything we've done in Calc 1 and up through Calc 2, we call it 2-dimensional rectangular system. So in a 2-dimensional rectangular system, 2 parametric equations will represent this particular relation here. But as you move through Calc 3 and you work in a 3-dimensional system, like the complex plane, then you will need 3 parametric equations to represent your single relation. So again, what you're getting here is a small introduction to parametric equations that you will continue on to if you're taking Calc 3. So let's kind of recap and let's define a circle, because we've only looked at a circle, sorry, of radius 1. So let's go ahead and let me get a new screen. And let's define a general circle. So the general parametric equations for a circle are x equals r cosine t and y equals r sine t, with t being between 0 and 2 pi. And another kind of common parametric that you'll come up with, let's suppose that the coefficients were not the same. So I'm going to call the first one A and the next one B. And we can still go between 0 and 2 pi. Well, think about that. That is no longer going to give you that perfect circle, because now the distance between the origin, on the horizontal is going to be A, and on the vertical is going to be B. So what do you think that's going to do to your curve if they don't have the same coefficient? So the same coefficient gets you that nice, neat circle. But what if we went like this? Do you notice you're no longer going to get a circle? Let's suppose B is, B is much bigger than A. Okay, this is what happens when you have an ellipse. So you may recall your equation for an ellipse. Okay, your standard equation for an ellipse centered at 0, we will keep it simple, but it would be y. Let's start with x. One. So that was your standard equation. So your parametrics for an ellipse would be like this. So there's another standard one. As we go through some examples, we might come back to using those today. So the next one is linear. So here we understand why it is nice, and we'll go through examples when we do derivatives, is to be able to take something that is clearly not a function, something like an ellipse, fails the vertical line test, not a function, and to go ahead and write it as two separate equations. Now, you must use these equations together in order for it to represent the ellipse. Each of them on their own does not represent an ellipse, but together they represent an ellipse. Okay, so we'll come back to those, but let's now think, well, what about linear? So we can actually take a linear equation and represent it using two parametric equations. You might be thinking, but wait, unless it's a perfectly vertical line, a linear equation is already a function. That's okay, because putting it as a parameter is actually going to give us more information than the linear equation would give us. So let me first define parametrics for linear equations. So you know what a parametric for a circle looks like. You know what a parametric for an ellipse looks like. Let's define a parametric for a linear. Yeah, there's a lovely 2-page proof of this in your textbook in section 12.1 if you're interested in where it's coming from. But what it's going to do, let's write it out first and I'll explain each term. X is going to equal X sub O plus AT, and Y is going to equal Y sub O plus BT. So let's define our X sub O, Y sub O, and our A and B. So the A and the B actually come from the slope. So if the slope of the original equation is B over A. Now think about that. B is the change in Y, so it makes sense that it's part of the Y equation of your parametric, and A is the change in the X value, so it makes sense A is part of the X equation. And it's the slope of the original equation that goes through the point that passes through x0, y0. A couple things we're going to do here, because you're also, I'm hoping you're sitting thinking, why would I need to take a linear equation and represent it with 2 parametric? That doesn't make sense to me. Well, let's work through it first, and let's do a few things with it. So we have these 2 equations. So the first thing you do is, how do you graph a parametric? So it's easier to work with the linears to learn how to graph a parametric. To graph a parametric, you can't just have an X and Y. We're going to go back to, first we're going to do traditional graphing. You first learn to graph, you just made a table of values. So let's make a table of values. And you can do this with any type of parametric, be it an ellipse, circle, any other type of curve, or a linear. But when you make your table of values, because a parametric has that third variable, we're going to use t. And we're going to start with t. Now, t is often defined. So let me give you an example. Of course, I started with the table without an example. Let's use an example. Let's say my parametric equations are x equals -2 plus 3t and y equals 4 minus 6t. And I'm going to define t. Now, when you're working in parametric, one thing I want you to realize is that t becomes your independent variable. X and Y are dependent. So to emphasize that, let's go back to that circle for a minute. All right? When we're working with basic x squared plus y squared equals 1 on our simple xy coordinate system, we know x is always the dependent variable and y is the independent variable, because we're often working with functions and we say y is a function of x. Notice when we did these graphs separately, like this one here, t on both of them became that dependent variable. Your dependent variable is always along your horizontal axis. And notice what we did. We put both x on one and y on the other on our vertical axis. So when you move to parametrics, x and y become dependent variables of t. That's an important thing to remember. So when you're given a parametric equation, like I just gave you right here, t will often be defined. And we're going to say, okay, this is our parametric for t being between 0 and 10. So when you're building your table of values, let's start at t. And we're going to start with 0, t equaling 0. So now, what is my x value and what is my y value when t actually equals 0? You just come over here to the equations, plug in t equals 0 for x. You see x is -2. Plug in t equals 0 for the y equation and you see y is 4. Now, we start at 0. We don't need to go all the way up to 10. We know we're getting a linear here because nothing is squared. There's no trig functions. If your two parametrics are linear, then when they come together, they're going to make a linear. So what we can do is just do a couple points. Oops, I don't need 0 again. Let's do 1, 2, 3. We'll do a few points real quick. And let's just quickly get some values. Now I need x being 1. So that's -2 plus 3 is 1. And I have 4 minus 6, -2. Now, t, sorry, not x was 1, t was 1. T is 2, so 2 times 3 is 6. -2 is 4. And when t is 2, I get -12, right? So what's that, -8? We'll do one more, though we probably won't have long enough to graph on it. At 3, I have 9, so that would be 7. And at 3, yeah, that would be like -14 or something. Okay. So we just need to graph 0, 1, 2. 3 points is probably more than enough. So -2, you're going to know right away if there's a mistake in any of your calculations. All right. 1, -2. And if I were to go 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, it would be about down here somewhere. So you can see we have a starting point, -2, 4. We're going to continue down. I am going to draw an arrow because we still have 4, 5, 6, 7, 8, 9, 10 that I don't have graphed. But notice I'm not putting an arrow up at the top because that's our starting point. When you graph parametrics, when you plot a point, you need to plot the t value of that point. So that's 0, 1, 2. Now, the big question, why use parametrics with linear equations? The main thing is it provides you with orientation. So in other words, it provides you a direction. T is a third parameter. You have your x, your y, now you have this third parameter t. With the equation and the ellipse, t represented an angle. But often with application type problems, t is going to represent time. That's why it's called t. At time 0, here's my first point. At time 1, at time 2. And that's what we mean by orientation. With a simple linear equation, you don't necessarily get orientation. What would be the linear equation for this? The non-parametric equation? Well, that's easy. Take your two parametrics. I mean, you can figure it out on the graph if you choose to, but we can do it algebraically like this. Here's the quick way to get your non-parametric. Solve for t. So that would be what? X plus 2 equals 3t. T equals x plus 2 divided by 3, right? And plug it in. Plug it in. So y equals 4 minus 6, x plus 2 over 3. So what is that? Look at that. Y equals -2x. That looks about right. Mine didn't quite go through the origin, but I'm also not using perfect grid paper. I probably should have turned on the grid paper for this problem. But that is correct. Y equals -2x. That is our non-parametric. And the issue with the non-parametric, again, it doesn't give you orientation of what's happening at t equals 0, t equals 1, t equals 2. This orientation where it's going down just happens to coincide with the slope. That's not necessarily going to happen all the time. And maybe you can see that in the next equation, next example here. So this example here that we just did is a nice way to take a parametric, see how to graph it using that third parameter, that t, and it also shows you real quick how you can take any, it doesn't have to be linear, any parametric and turn it into a non-parametric equation. All right, so this is the parametric equation representation of y equals negative 2x. Here's the thing, as become really clear in the next example. There are many, many ways to use parametric equations to represent y equals negative 2x. So let's take a look at a second example dealing with linear, and then we'll do an example with nonlinear. So suppose I was given a line that we know has a slope of 1/3, and it goes through a point 2, 1. I want to find the parametric equations, not the regular one, just the parametric equations. Okay, just use your formulas. X equals x sub o plus at, and y equals y sub o plus bt. So what does that mean? Well, that would be x equals, what's the x value? 2. All right, remember slope 1/3. Let me go back up to the formula here, right? B over A. So slope is represented as B over A. In other words, you want the change in X part. So that's going to be 3 plus 3t. And Y is going to equal 1 plus t, right? Because clearly in this slope, you see A equals 3 and B equals t. X sub o is 1, y sub o. X sub o is 2 and y sub o is 1. All right, well, there you go. You've got your parametric equations. That was fairly quick. All right, no issue there. If I were to graph them real quick, here, I'll keep this one in red, and we'll just graph real fast. Let's keep it simple. Let's go 0 to 2 or something like that. 0, 1, 2. 0 is going to give you x equaling 2, y equaling 1. 1 is going to give you x equaling 5, y equaling 2, and 2 is going to give you 8, right? 2 times 3 is 8, yeah. And y equaling 3. All right, do a quick sketch. I have 2, 1, 5, 2, 8, 3. Now, don't forget your t. That's t equaling 0, t equaling 1, t equaling 2. So my orientation is like that. All right. So let's try something else, because that is not the only parametric equation. Would you all agree that let me fix this. I don't know why that says that. That was B is 1. I'll do this one in blue. If A equaled negative 3 and B equaled negative 1, would you have the same slope of 1/3? And if that's the case, Let me get rid of that for a second. Then could your parametric equations be 2 minus 3t and y equals 1 minus t? Still get a slope of 1/3. All right. If that's the case, now plug in 0 for t. I get 2. And plug in 0, I still get 1. But plug in 1. Now don't I get -1 and, right? Wait a minute. Plug in 1. -3, I get -1. Plug in 1, I get 0. Plug in 2, -6. What do I get? -4, yeah. And plug in 2, I get -1. Graph it real quick. So I still start the same starting point. 2, 1. That's t equaling 0. Then I have -1, 0. T equaling 2. And then I have -4, -1. What changes? Orientation changes. We're now going in this direction. Okay? So when dealing with parametric, one thing to realize, when you are given limited information, such as slope and point, without a direction or an orientation or anything along those lines, there are actually infinitely many parametric representations of that information, because not only can you use 3/1, 3:1, or -3, -1, we could use 6 and b equals 2. That would come out to 1/3 as well. There's a lot of different representations we can get for parametric. So be careful with some of the problems you do. They might mention orientation. But notice you have the same line, but the parametrics give you a piece of the line along with an orientation of the line. So this set of parametric equations is a little bit different from this set of parametric equations, even though they represent ultimately the same actual equation. If you were to solve for t and plug it in, if you were to solve for t for the x and go ahead and plug it in for y, you're going to get the same equation on both sets. But their parametrics are different because they're giving you different information. All right, so let's move on to a parametric of a curve. And let's do this one. Okay, and let's take t between -10 and 10. All right, so first thing I want you to do is let's just sketch it and see what this looks like, okay? Let's make a sketch. So I need to do a quick sketch. Let's do t, x, y. I'm gonna put 0 in the middle here just to make it a little bit easier because of where my range of values are. What's my x value going to be when t is 0? X is 2, 0. I'm going to go a little bit probably on either side. Let's see what happens. Plug in -1. Oh, well, -1 when I square it is going to give me 1. 1 plus 2 is 3. And -4. Oh, I meant to put -1 up here. Sorry. 3, -4. So let's put +1 on this one. That makes more sense. You're going to get the same x value, right? -1, +1 is not going to matter. It's going to be 3. But your y value is now going to be 12. So right off the bat, you can see what we're having sketched, right? So if you look at the original parametric, that t squared should tell you, hey, I probably have some sort of a parabola, right? Because we know things that are squared are parabolas. That doesn't change. So let's do it. 2, 0. When x is 3, well, it's going to be negative. When x is 3, I can go down to -4 or, hold on, positive 12. Yeah, clearly I can't do my math today. This was 4. Right, and as you go -2 and +2, you're going to get these values that are going to keep coming out, and what you have is this non-function parabola, right? Now, you can certainly try to find the equation for it by saying, all right, because you can, in this case, I'd probably easier to solve for t equals y over 4. So then x would be y over 4 squared plus 2, right? X equals, not y, x. So x equals y squared over 16 plus 2. And, you can manipulate it any way you want, but you don't have a function. And not having a function causes some difficulties when we start to do other things. Not necessarily, but, things like implicit differentiation and stuff like that. So let's talk about, and we'll come back to this one in a minute. So this is x equals 1/16 y squared plus 2. That's that equation. And this is also the parametric equation. Do notice where you're starting at -10. So we're kind of moving this way orientation wise, right? And because at -10, you're going to get those negative values. So it's kind of moving like that. But I want to talk derivatives for a second because, well, not that you can't take the derivative, because you all learned in Calc 1 something called implicit differentiation. But normally, you take the derivative of a function like f of x that only has x's in it. Do you remember? So this is a recall from Calc 1. Implicit differentiation. Implicit differentiation, but you don't really, you kind of need in that one, because to solve for y, you've got a radical, it's not going to really work. 1/16 y squared plus 2. So implicit differentiation says, all right, to find dy dx, dy dx of x is just 1. Dy dx of 1/16 y squared is 1/16 times 2 y to the first, but then times dy dx. Whenever you took because technically the derivative of x is 1 dx dx. We won't write dx dx. And then the plus 2 goes away and becomes 0. But then you had to come over here and do dy dx, and you had to solve for dy dx. So this ends up being 1/8 y. So you move it to the other side, and becomes 1/8 y. So y over 8 times dy dx, you multiply it by the reciprocal of y over 8, which is 8 over y. And that's what your derivative is, which if you recall, becomes much more complicated the more y's and dy's you have in the problem. So what we need is a way to differentiate our parametric equations. And that's all we're going to do in Calc 2, is differentiate those parametrics. I'm going to save integrating parametrics for Calc 3. So remember, what was our original? It was, let me put that down. Can't find, there it is. T squared plus 2 and 4t. So we had t squared plus 2, 4t. Ultimately, we want to find dy dx. Well, would you agree, because we have this third parameter t, we worked with this a little bit when we did related rates in Calc 1. Couldn't you say that times the dt dx? Would you agree that because I can cancel the t's, these two relations equal each other? Okay, so this is a way I can introduce the dt because I need dt because there's a t in my parametric equation. The problem is the dy dt part's perfectly fine. Find the derivative of y with respect to t. That's just going to be 4. That's going to be easy. But I really don't want to find dt dx. So I'm going to do a little algebra on this and write it as dy dx equals dy dt. Instead of multiplying by dt dx, I'm going to divide by reciprocal. And this is the way you are going to differentiate parametric equations. So let's see how easy that is. Dy dx equals dy dt. Well, here's your y. What's the derivative of y with respect to t? That's just 4. And then dx. What's the derivative of x with respect to t? 2t. Just 2t. So our derivative is just 2 over t, which if you wanted to put it back in terms of x and y, we know that t equals y divided by 4, 2 over y divided by 4 times 4 over 4 equals 8 over y, which is exactly what we got when we did our differential or implicit differentiation. This just happens to be slightly, I find the parametric on some of these that can get really complicated with differential just to be much easier. Let's take a look at another one. So let's do if x is t cubed minus 3t, y equals t, I want you to find dy dx. Okay. Well, first part is dy dt. Well, that's just 1. Dx dt, 3t minus 3. And then if we want to put it back in terms of y's and x's, well, we know y equals t, so it's just 1 over 3y minus 3. Done. Go ahead and now, to do implicit differentiation, number one, you got to turn your parametric into a non-parametric equation. So knowing y equals t, x equals y cubed minus 3t, I just plugged in, right, that into there. Now I can do implicit, which is going to give me 1 equals 3y squared dy dx minus, oops, I forgot to make that a y, minus 3 dy dx. Then I've got to solve for dy dx. So you have 1 equals dy dx times 3y squared minus 3. Then I got to divide by it. So dy dx equals, not that this one was that hard, but you may recall they do get much more difficult. It's exactly the same. Okay? And the last thing I'm going to do is just kind of go back to those circles. But this time I'm going to put it between pi and 2 pi. Those parametrics that, how do you know they're a circle? Well, x has the cosine, y has the sine, and the coefficients are the same. Coefficients were the same, you'd have an ellipse. So what I want to do is verify the equation of the circle. So yes, you can look at that right now and guess what the equation of the circle is, but I want to verify it using our parametric equations. In other words, I want to do the long way of taking that and turning it into. So to do that, I'm going to start with x equals 3 cosine t, and I want to solve for t. Okay, that's x over 3 equals cosine t. You got to use inverse functions. T equals cosine inverse of x over 3. Let's think about that. Okay, we are in which quadrants if I'm going from pi, so think of unit circle. If I want to go from pi to 2 pi, I'm looking at this, right? So I'm in the third and fourth quadrant. I want to take this t and plug it into the other equation. So now I get this crazy composite trig function thing, sine of t, but t is cosine inverse of x over 3. Sorry, I forgot the -1 when I wrote inverse. So this is going to take you back to something else you did in pre-calc 2 or your trigonometry class. Draw your right triangle. Okay, we know we're in quadrant 3 and 4, so hey, we can go ahead and put one in quadrant 3 and 4. The cosine of x over 3. So this is my t value. Cosine is adjacent over hypotenuse. Adjacent over hypotenuse. And obviously that x would be negative. To get sine of that same angle, I'm missing the third side because sine is going to be opposite. I get the third side by just doing your Pythagorean theorem. 9 squared, right, equals negative x squared plus this side squared. We don't know what that is. So if you remember, you're going to do 9 squared, the square root of 9 minus x squared. So you're going to have square root 9 minus x squared for that side. Okay, and if you're not sure why, draw yourself the triangle, 3 put an x there, and I don't know, put a y there, and solve for y, right? Y squared plus negative x squared equals 3 squared. Y squared equals 9 minus x squared, so y equals square root. Okay? Whether that's negative or positive, you can see they're both negative because we happen to be in the third and fourth quadrant. So all of that, so what does that give us? Y equals 3. We determined the sign of t is now negative square root of 9 minus x squared over 3. 3's cancel. What do I have now? Y equals negative square root of 9 minus x squared. Well, that doesn't really help me. Let's square both sides to get rid of that radical. Remember what we're trying to do. Verify that the equation of the circle. Well, if I square a negative, it becomes positive. If I square a radical, the radical goes away. Move the x squared over. Forgot to square that one. Again, verify. I know you, by definition, can look at the parametric and know what the equation of the circle is, but this is the work you need to do to verify that equation of the circle. All right, so that concludes our intro to parametrics, something you're going to work on a lot in Calc 3.